Before we get started, if everybody could please raise your hand. Either hand works. All right, come on, let's go. All right, so anyone who didn't follow the seating instructions, please lower your hand. All right, all right. Still looking pretty even, I would say, between people who know web and people who know native. So that means as we go through this, yeah, put your hands down, please. We'll probably give a little bit of remedial education on both sides of the house, just so people who only know web aren't lost when they're talking about the C stuff. People who only know C aren't lost when they're talking about web stuff. So I apologize if any of this is review for you. All right, so I'm Justin, this is Tyler. We're here to talk about WebAssembly. So our talk today is not about how to break out of the browser in WebAssembly or use WebAssembly type bugs to end up exploiting things in the browser. That talk was Natalie's talk, and if you're interested in that, you should go see it 3 hours ago. It was a really great talk, and maybe you can catch the recording of it later, but we're only going to talk about the application security side of that. So if you are a web developer who is trying to implement some new WebAssembly things into your existing website, what kinds of security problems could you cause and do you need to worry about? As an attacker, when you're looking at a web page that includes WebAssembly, what can we use that for from an attack perspective? So that's what we're looking at in this talk. So in order to do that, we have to talk about how WebAssembly works and some other kind of introductory tooling stuff so you can understand later on when we go into the different exploits what's actually happening under the hood. So if you saw Natalie's talk this morning, that part will be review, but then the other stuff should be pretty fresh. Skip one. Both went at the same time. So in short, what Wasm does is it allows you to take code written in something else. We're going to only talk about C code here, but you could do anything. Compile it, and then take that binary and run it in your browser. What that gives you, for one, you didn't have to rewrite that code in JavaScript. And two, it's much faster than doing the same thing in JavaScript. So you can see here, WebAssembly on the left, getting 30 frames per second at face recognition. JavaScript on the right, getting 2 frames per second. So much faster. There's a lot of different things that it's being used for right now. I'm only going to highlight a couple of these right now. The archive.org has this really cool thing where you can go play old console games and old arcade games on their web page. And they do this by, they didn't rewrite an assembler or re-implement the games in JavaScript. Instead, they used WebAssembly to compile an existing emulator that already knew how to emulate those games, wrote a little bit of wrapper code around it, probably more than a little bit, to handle the display and controls and such, and then they can run all these games that already had previous emulators. Other thing here that's going to be interesting to this audience is there already been seen crypto miners in the wild that have been using WebAssembly because it's much faster, so you can mine more coins. WebAssembly isn't just about the web, though. There's lots of really crazy things that are kind of up and coming. Everything on this is kind of very early stages or experimental, but it's important that you know that there's a lot more that's going to be happening soon. So Browsix is essentially implementing all of POSIX in WebAssembly. So if you had a Linux program, you would be able to run it in WebAssembly and have all the things like files and stuff work in the browser. JS Linux takes that one step further and actually emulates an entire operating system in the browser. So if you want to run a copy of a recent Linux or something like Windows 2000, you can run it in your browser, and it runs all with Wasm. Runtime.js, going in a different direction, is a microkernel. So the idea is instead of running a whole OS somewhere, you would just run this thing, and all it has in it is Node and Wasm. So then, you can drop the whole OS and just concentrate on running stuff. But that also means that it's all running in ring 0, right? Because it's all its own kernel. Nebulet is very similar, except without the node. So we're just going to run Wasm straight up ring 0 as its own kernel. Service is very interesting. So instead of trying to start a new OS, they're going to allow you to run WebAssembly things that hook into your Linux kernel. So then you can directly access memory and stuff in there, and it's very fast. Sounds like a great idea. Crane Lift is actually going in reverse. So you can take a Wasm program, the compiled binary, and then turn around and turn it into a real machine binary that would run on like x86 or ARM. And lastly, and probably the most useful of all these, is eWasm. So Ethereum is a cryptocurrency that has its own language. And so the idea is that you can compile things with this language and then they run on the blockchain with all the stuff. It's pretty interesting, except that Solidity is terrible and the EVM is terrible. So they're working on switching it to running Wasm instead. So then you can write your smart contracts in whatever language you want, and then they run in Wasm on the blockchain. Cool stuff. So any of you who have been around computing since about 2001 or so may remember that we used to claim that there's these cool things called Java applets, and they're sandbox, and they run in a virtual machine, and they run in your browser. You can write them once, you can run them anywhere. And you can put them in other things besides browsers. This is all the stuff that a Java applet claimed to do 20 years ago. And now we're doing it again. I really wonder if the Wasm folks knew that they were re-implementing this stuff, or if they are surprised that this is actually happening. All right, on to what WebAssembly actually is. It really probably should have been called something else, like Web Bytecode or something. There's a virtual machine, so don't think about VMware, more like a JVM. So a special purpose machine that doesn't really exist, but we're going to emulate that machine. And it has a very specific set of instructions. It's a very small set. And then there's a binary format that the instructions for this machine are in. Then we have compilers that can target that new virtual machine. And so then you can have code that was written in other things and compile it to WebAssembly where it will run. Way faster than JavaScript. It's already in pretty much every browser that people use on a regular basis. But as we talked about earlier, there's no reason we can't take Wasm and put it in other things as well. Let's talk a little bit about the mechanics of Wasm. So we have instructions. They live in their own spot. These are the machine code, essentially, for Wasm. And the machine that runs Wasm doesn't have any registers. So instead of registers, we have the stack. Don't think of the C stack. That's totally separate and has to happen later. This is the stack within WebAssembly, and it replaces registers. So the idea is that every operation will push or pop its values to and from the stack. Here's a very simple example. So first line, module means this is a program. And the next line, line 2, we are declaring a function called add. We give it 2 parameters, x and y, and we're saying it's going to return a value. All those are 32-bit ints. The line 3, we say get local x. What that does is take the value of x and push it onto the stack. Get local y, push it onto the stack. And then i32 add is going to pop 2 values from the stack because add takes 2 operands, and then push back the value of that addition onto the stack. And the last line here is export. What that means is that this add function will now be available to whatever it is that's embedding your Wasm system. So in most cases, your browser or JavaScript. Yeah, I don't think we can. WebAssembly doesn't have access to your computer's memory. It has its own memory that gets emulated. And this is called linear memory. It's just its host thing could implement this however it wants, but from WebAssembly's point of view, it's an array of bytes, integers, whatever you want, and it can put things in there and take them out in random access. That's all it can do with it. There's no way that you can see the real address that something's living in from the WebAssembly side. You just know about the values that are there and their indexes in that array. Everything in there is untyped. So the other piece of the puzzle here, there's a few things that maybe will become clear if you're well into the C world. For starters, since WebAssembly runs in its own space, so it's not like, say, x86 and ARM, where your instructions are interleaved with your data in the machine's memory. Instead, it has a separate bank of memory for instructions and a separate bank of memory for data. So there's no way that we can have like a pointer that goes to an instruction. But we write C programs like that all the time, and so we need a way to implement that. In WebAssembly, they made this thing called a function table. So all a function table is you can declare, hey, I'm going to want an indirect call to a function somewhere, and then that goes in the table. The table just has numerical indexes. And then later on, you can say, okay, I want to jump to function number, decide this at runtime, and then later it goes, looks that up, and does that. Let's take a look at that in code. And if you can't read this in the back, I'm going to walk through it. It's not necessarily, you don't need to really understand this to get to the rest of our talk, but it is important. So again, we have a module. We're going to declare a type of type function with a result. So what we've done here is we've said we're going to have function pointers, and they are going to return an int. They're not going to have any other parameters. Then we're going to make this table, table2anyfunc says we're going to make a table that has size 2, and then element f1 and f2 on line 4 says we're going to add 2 new entries to this table. They're called f1 and f2. On line 6, we're going to declare what f1 actually is, and note that it has the same signature that we talked about before. Returns an int, that's all it does. In this case, we're just returning a number. Same with f2. Here, we're going to actually call something. So this is a function. We are taking one parameter and returning one thing. And in here, we're going to say get local I, so get the value of the parameter, push it on the stack, and then call indirect some type. So now, call indirect is going to pop the thing off the stack that we just pushed, which was the value in the parameter. And then it's going to go look up in the function table which function is that, and then go and actually call it. So just another way to show that. So when you use call indirect, it's going to pull something off the stack, go look up the value in the stack of the function table. The function table knows the address of the actual thing it's going to call, and that's what makes the call. So everything we've talked about before this has just been about Wasm. We haven't talked about the browser at all. So we need to talk a little bit about what Wasm means while it's living in a browser. Wasm can't talk to the DOM. Wasm can't read your memory. It can't write to the screen. It can't do anything on its own. It's totally sandboxed off from all that stuff. If you want Wasm to do anything other than spin your CPU, you have to declare some imports or some exports. The most obvious example of this is functions. So we declared the export for the add function, and then that meant that JavaScript could call that add function, and it would run the Wasm and then return the value back to JavaScript. You can also import and export the memory. JavaScript is able to look at the linear memory, and you can also share that linear memory across multiple running instances of Wasm if you want to. And the tables can also be shared across multiple instances of Wasm if you want to. This means that you can do things like kind of a multi-threading thing where you've got a web worker running something and another web worker running another thing. They can share memory if you need to. They can share libraries if you need to by sharing a function table and so on. Inscriptin is, I guess, a tool chain or an SDK. And its point is to create Wasm binaries for you out of other things. And we're going to talk about C and C++. It's built on LLVM and Clang. It includes all your expected built-in C libraries. And it also makes it really easy to integrate your Wasm that you've just produced into a web page by automatically generating JavaScript and HTML for you that will handle the glue code that helps the two pieces communicate. There's a whole bunch of other things that Inscriptin adds as well, but the only things that we're going to talk about here are these two things called EMASM and Inscriptin run script. Those are both two different ways. They're slightly different, but the idea is that you can use those to run arbitrary JavaScript from inside Wasm. That's going to be really important later for some of the tricks we're going to do. If you want to know more about Inscriptin Wasm, since Natalie's talk is over and you can't go see that anymore, you can go read the spec. You could also, this PDF here does a really good job of, like, if you're a reverser and you want to know like the nuts and bolts of how the binary format works, it does a great job of running through what a WebAssembly binary looks like and how it all works. I wish I had that PDF before we started doing this research. So we're going to talk about old exploits, and I have a lot of choice, vintage, well-tested memes to go along with these slides. So we think that a format string attack will work just fine. For the web people who don't know C, I have to cover what a format string attack is. So there are a family of functions in C that take a format specifier where you can say, okay, I'm going to have some values of some variables that go into the string, and then the values get filled in at runtime. The way that it works, if the user can control this format specifier, then the user could add in extra lookups for variables that didn't actually exist. And because C loves to let you shoot yourself in the foot, it just starts popping new things off the stack and putting them in the string. There's also a way to write things to things because they added this %n that lets you write. So essentially what it means is if there's a user that can put in, that can taint the value of the format string specifier, then they can arbitrarily read and arbitrarily write for the most part. Go back one. We don't have a POC for this yet, so you can tell me to get out later, but we think that this will work. Integer overflows. Overflows are present in a lot of languages, but for people who haven't heard of them, if you have an integer, it has a maximum value in any programming language. So if you do an operation that would cause the value stored in that integer to be higher than what the maximum value was supposed to be, then it rolls around to the back again. So if it's a signed type, then you end up in negative numbers. If it's unsigned, then you end up in a low value. This is important for one, because you might, if this was a value that was like your bank account, you could flip it over or withdraw something that you shouldn't have been able to, things like that. But also it's a gateway sometimes to buffer overflow exploits because you can change the expected value of how long an array was supposed to be before it gets created, things like that. So just in the plain C world, Wasm isn't doing anything to defend you against these. So if you just have a straight up C integer overflow, it's still going to work fine. The interesting part here is that now we're throwing in Wasm and JavaScript into the mix, and they all have their own integer types with their own maximum values, and everyone's different. So I'm not going to list off all the different types in C. There's a ton. Wasm has int32, int64, float32, and float64. JavaScript has 2 to the 53 minus 1. So what that means is if we're sending a value from JavaScript to Wasm, the Wasm value was declared as a 32-bit value, but the JavaScript that we send is, say, 2 to the 40, then what we've just sent in already overflowed before we even started the C. And so then, there's going to be a problem there. We had a demo of this, but it was boring, so we didn't put it in. You could also overflow in the other direction. So if the Wasm was too big for what we return back to JavaScript, then you could have the same problem once it gets back to the JavaScript. Buffer overflows. So again, for people who are web people, a buffer overflow happens because C doesn't check the bounds of memory when you have an array. And so if you tell it to write more things than there is space in the array, it just keeps writing through into other things in memory. This still happens perfectly fine in Wasm. You're not writing in kind of regular memory, you're overwriting things in that linear memory. So whatever was in there, we can continue to overwrite. The kind of simple case for this is if there's a value in memory that you wanted to change because it means something important in the context of the application. So something like a privilege level, your account balance or whatever, if we can find a way to overflow into those, then we can change those values, which is useful. The other thing that these normally are used for in C is to run arbitrary code. Now, running arbitrary code in Wasm is much harder because we don't have these function pointers and return pointers and all these other things that we can try to override and then put our code. Furthermore, we can only do this in linear memory, which is never executable. So we can't write some executable code and then jump to it. So we need some other things to do. We'll talk about that later. If you try to go past the bounds of linear memory, into something else that the browser would have, it's supposed to give an error. I think Natalie's talked about a few cases where that wasn't actually the case in a browser implementation, but from a general Wasm perspective, it's supposed to work fine. With all that being said, there are still some interesting things we can do with buffer overflows that get us some interesting kinds of code execution. We'll talk about that in a minute.
Okay, I have a pretty simple demo here, which is kind of the most basic type of buffer overflow. So here on line 6, we're using this em_js, which we talked about earlier. And this is allowing us to actually define JavaScript inside of our native code. So here you can see that we're creating a function called overflow alert. And we're saying that it's void, it takes no parameters, and that it just creates an alert box that says overflow. And then here in our main function, we've got two buffers. One is ABC, one is 1, 2, 3. And then here we've got a string copy where we're putting way too many Bs into this boff1. And then then we're going to check the value of boff0. So if boff0 is ABC, then this string compare is going to return 0 and nothing is going to happen. If there is an overflow and it's not ABC anymore, then the string compare is going to return some value. And if it does, then we're going to get this overflow alert box. So if we see the overflow alert box, that notifies us that there was an overflow. So I can go into my virtual machine. And we're going to use Inscript's emrun, which allows us to just sort of like, it's kind of for like testing code. It's a basic web server kind of a thing. And we can just run our boff0.html file, which we compiled with Inscript, and see if we get our alert box. And we got an overflow.
All right, so there are way too many different types of bugs in C for us to cover all of them. We'll just briefly cover the rest of the existing C bugs and kind of give you our take on whether we think they're going to be useful or not from an attacker's perspective. So talk to race conditions, that stuff should all be just as before, with the caveat that threading is not very mature in Wasm yet. Same story with timing and side channels. We think that heap-based arbitrary writes will also work in the context of linear memory. We don't have a POC for that either. Things that won't work are your classic buffer overflow where you jump back to the code you put in. Things like ROP won't work because we can't arbitrarily jump to places in memory. And as it's supposed to work, you shouldn't be getting any information from the browser. For example, when you declare your memory, it's supposed to be all zeroed out when it gets to Wasm, so you can't expect to read uninitialized memory and get something interesting there. On to the new exploits. And Tyler assures me that all of the memes we have here are really fresh and everyone in the 15 to 25 demographic will get it. So, off to XSS. So, let's talk about XSS for a minute. Since we gave all the web people the remedial C stuff, we have to do the other way too. XSS means that we're running arbitrary JavaScript in the context of a web page. Now, if you're not that familiar with web stuff, you might think, oh, big deal, I made a pop-up, or oh, big deal, I can steal a session token. Those things are things you can do. But what XSS really means you can do is you can control everything that user could have done, and a lot of things that maybe they didn't even know they could do, in the context of that website where you got XSS. So if it's a bank and I get XSS, I could use all the functions to transfer money out. If it's a social media account and I get XSS, I could post social media stuff on your behalf. I could change your password, et cetera, et cetera. So XSS is a real thing. And in the WebAssembly world, it's actually even more important because the JavaScript has the ability to read the linear memory that it's allocated. It has the ability to start and stop Wasm. It has the ability to modify Wasm code. I don't think you can modify it when it's running, but you could stop it and then restart it with your new modified version. So you should never consider that code that's running in Wasm is somehow protected from the browser. If someone has XSS, they'll be able to do anything they want to the Wasm that's running, in addition to anything they want to the rest of that site. No, let's go back. So now that we know what XSS is, let's come back to what it means to do buffer overflow here. So if there is an array that is written to the DOM, and we have an overflow somewhere, and we can overflow the value that would have been written to the DOM, then we have XSS. Pretty much all there is to it. We used to be, our first demo of this stopped working like halfway through our research, and we were really worried. But it was because we were overflowing a literal, which normally is really hard to do. And they moved where literals go in an updated version of Inscript, I think, to go below us in the stack, and so we couldn't overflow it because we can only overflow up. Other interesting thing here is that your typical way to find XSS is to look for reflection. So I put in an input in some web page, and then I look to see if that gets reflected. That same input that I put in comes out somewhere else, and then I can try to see if I can manipulate that to run JavaScript. We can do XSS without any reflection here because we're actually putting in a value somewhere over here, using it to overflow something that shouldn't have been writable by the user, and then that's what actually causes the XSS.
Okay, so I have another example here for how we can use this buffer overflow to XSS concept. So for this example, we have this bof function, which the extern keyword is going to let us call it from JavaScript. And this function is going to take two parameters. It's going to take p1 and p2, both of which are just character pointers or character arrays. And we've got two character arrays, bof1 and bof2, both of which are 16 bytes long. And then we've got two unsafe string copies from p1 into bof1 and p2 into bof2. And then here we're using this EMASM again, where basically we're just getting this element by ID. We're getting an element called SSX, and we're setting the inner HTML to this pointer stringify function. The pointer stringify is going to take an index into linear memory, and it's basically going to turn that into a string. And it takes these two parameters, 0 and 1, which are defined here, which is bof1 and the length of bof1. So essentially what we're doing is we're taking p1, copying it into bof1, and then we're taking bof1 and we're printing that directly to the DOM. And here in my example page, yeah, so here's what the code is going to look like from the JavaScript side of things. And the reason why this can be especially dangerous is here we're calling our bof function, and here we've got a static string which we're passing in as p1 and some user-defined string as p2. And the developer is thinking to themselves, I'm putting a static string in here. It's totally safe. I don't have to do any kind of encoding. I don't have to do any kind of sanitization. I wrote that string. I know what it's going to be. But because there's an overflow in the code, we can taint this string with user input. So we can see here, when we smash our like button, we see our static string is written to the DOM. We can put in a couple of A's, and nothing happens. We can put in a couple more A's, and we can see that now we're actually starting to write user input over to the DOM. And now we can go to the end of our thing, and we can try to make some kind of a XSS payload. See if I can do this right without messing up. And we got an XSS box.
All right. So that's kind of basic. It's still cool, but not that technically interesting. We know we can overflow values. The reason we went over a bunch of details about how function pointers work is because we can do some interesting things there too. So we know that function pointers in Wasm aren't really pointers. They're integers to this table that does the lookup. And we know that when we use the call indirect stuff to execute a function pointer, that's going to pull a variable, get the value, go look up from the table what to call, and then call it. Now we've just shown you that we can modify what's in a variable via an overflow. So you should be able to guess what comes next. Inscript, when it adds things that you're using, it puts them in the function table. So if you used Inscript and run script in your program for some benign purpose, it's going to be in that table so we can call it dynamically as well. It has a signature, it returns nothing, and it takes, that's supposed to be const char, but keep in mind that this is Wasm, and Wasm only has 4 types, so really that's integer. So, and then when it takes whatever string is pointed to by that and executes it. So if we can find a way to pass whatever we want to this function, then we win, we get XSS again. In order for this to work, there's a few things that have to hold. So it has to be used. Inscript and run script has to be already in the program that we're wanting to attack. That means it's in the function table. There has to be a function pointer somewhere else in the program that has the same signature as Inscript and run script. So returns nothing, takes 1 int parameter. And we have to be able to somehow overwrite that function pointer. We're going to show you buffer overflow. Any other trick you've got that can arbitrarily rewrite some value will work.
Okay, so here we have another example of, yeah, it's a good meme, right? We have another example for our overflow. Does this look okay? Yeah, this looks pretty good. Okay, so the the scenario here is we've got some kind of a file processor, which is going to take a file and it's going to run some kind of a processing algorithm on it. So we have this file processor struct, and the struct is going to have a character array of 64 bytes, and that's going to represent the file that we're uploading. It's got a file length, and then it's got a function pointer for the processing algorithm, because, say there's a couple of different processing algorithms that we might want to try to run, and so this is going to let you dynamically choose between which processing algorithm you want. Here we have our trigger function, which is just going to call the processing algorithm, and it's going to pass the file to it. So it's just going to call that function pointer. And here we have our machine learning blockchain processing algorithm. The next iteration is going to be IoT. It's a pretty cool startup. You guys should check it out. So here in our function that we're exporting, the overflow, we're declaring a file processor. We're setting the algorithm to our machine learning blockchain algorithm. And then here we're doing a mem copy from the payload, which is just the parameter to this function, into the file. And then as you can see, we're mem copying 88 bytes, whereas the file is only 64 bytes. So this is a pretty classic buffer overflow. And then here, this is important, we have Inscript and run scripts, which is, in this case, it's just saying that, there's some kind of a log, which is saying, congratulations, you uploaded the file correctly. But this has to be in here because this is putting it in the function table. And then finally, we're just going to call our trigger on the function pointer. So we have a payload, which we're going to, this is the file that we're going to upload. So we're going to have alert XSS, and then we're going to be filling in some spaces just to fill out the rest of the 64 bytes. And then here we're filling out the rest of the struct. We're filling out 4, which is going to be the file length. And we're filling out, this is the integer 5. Now, as Justin may have mentioned earlier, the file, the indexes in the function table are constant, not just across execution, but across compilations. So I've compiled this on 3 different machines, and every time the index of Inscript and run script is index 5. So 5 is the index of Inscript and run script. And so hopefully our function pointer overwrite, instead of calling the machine learning algorithm that we wanted, it's going to call Inscript and run script, and it's going to pass alert to it. So here we have another example where we can choose our file. And that one. Cross your fingers for the demo gods. And we got an XSS box.
So more details about this. There's no reason we have to go for the XSS here. We could instead have used this to call some other function that was important with values that we wanted. So if there was a function to change my password or something like that, we could call that and then give it the values we wanted to then do what we wanted it to do. We can do this to anything that is in the function table and is, has the right signature that is something we can overflow to. So Jonathan Foote, if you're in here, raise your hand. No? Okay. So he made a blog post, he works for Fastly, that talks about some very similar techniques. He was doing, instead of using buffer overflows to make his overwrites, he was doing it via type confusion or deserialization type bugs, but it's the same endpoint. So he's using those kinds of tricks to end up with a function pointer that calls something he wanted to call instead of what the program was originally going to call. Looked like he was doing it about the same time as we were. So I know that all you C people don't care about XSS, even though I tried to explain how important it is. So we had to give you some RCE, right? So if the server's running Node and you do the exact same thing we just showed you, then what does XSS mean in Node? It means RCE. So we should be able to run whatever we want on the server if we have these same vulns in place.
All right. Last example. It's the exact same file processing that we have before, only now the payload is slightly different. Instead of the XSS payload, now we're requiring a child process, and we're going to be executing some application of our choice. And the rest of it is identical. So we're going to go over to my virtual machine here. Let's see, not this one. This one. And we're going to just run our Node server. Go back over here. Hopefully this is still the same IP address. Nope. Let me try incrementing it. There we go. Okay, so here's our file upload. So we're going to choose a file.
So now we're not just running this locally in the browser. We're uploading this to Node, and Node's going to run it.
Upload a file. And demo gods were not kind to us. Going to try this one more time. If it doesn't work, I have a recording of it working. This one.
Yeah. All right, so now you guys have seen some cool bugs. Let's talk about what we can do about it. So one thing we can think about is, are there things that Inscript could add to make everything more safe? So there are things that are kind of out of their scope. So for example, it doesn't really make sense for them to look at things like NX and stack canaries and things like that. Even though those are valid C mitigations, they don't really apply in the Wasm world because the code and the data are already not interleaved. Some protections they could add, something like address space randomization. So when we put things in the function table, the order that they are in there is determined at compile time, which is bad from a security perspective because it means that your exploit will always work, except when it doesn't, like it should. But it should always work. So there's no reason they couldn't make it so those values, there was a much larger set of values to choose from, and they were randomly determined at runtime. Then you wouldn't be as easily able to mess with function pointers in the way that we're showing. It would be nice to also have some library hardening. I don't know that anyone uses %n in format strings anymore. It looked like the heap implementation that's being used is kind of an older heap that doesn't have a lot of heap mitigations in place. So there's some improvements that could be made in Inscripted. Things that work really well, control flow integrity. So if you're not familiar with control flow integrity, there's a switch you can, I think it's Clang or LLVM, not sure where it happens, but you can turn it on in there at compile time. And what's going to happen is it kind of generates a mapping of all of the possible flow states between different functions in the program. So these are all the things that could ever happen. And then if at runtime you are off the map, it just crashes. So if you turn that on, our function pointer tricks won't work anymore. The other thing that's effective here already is the way that Wasm works to not allow us to jump into arbitrary things. It means that there's no way to do something like ROP. The best we can do is call individual functions one at a time. So we spent a lot of time researching this and then found that buried on the security page of the WebAssembly design specification in the 3rd paragraph in the 4th section, like they talk about, oh, and by the way, we probably didn't protect against this and this and this and this and this. Almost everything we just talked about in this talk, the WebAssembly people did talk about and say, yeah, we probably didn't defend against these. It would be nice if they made this much more obvious instead of a buried paragraph that's all long and wordy, like a nice bulleted list of, you still need to fix all of these kinds of C issues, this and this and this and this. So I'd love to see them fix that. If you're an application developer and you want to try to make your code safe, the first step, if you cannot use Inscript and run script, you will be much better off. If you have to use it, you have to use it. But just like any language where you have something that's like eval, like you want to avoid that if at all possible. Even if, as we've shown, even if you don't have a user-tainted way to get into it, if there's an overflow, we can still call it. If you don't use it in your code, we can't call it, and so then it's not useful as attackers. The optimizer. So sometimes when we would do things, they wouldn't work. And why did my demo stop working? Oh, we compiled it with the optimizer turned on, which changed the way everything worked. And in some cases, it removes functions or inlines them, or I don't even know what's going on. But there's a lot of times when we turn the optimizer on all the way, some of our stuff doesn't work anymore. So turn on the optimizer. It's not on by default, but use it when you compile. Control flow integrity, we talked about how that works. There is a performance penalty when you turn that on, but depending on what you're doing, maybe you can handle that, maybe you can't. But at the end of the day, even if you do all those things, there's still plenty of C bugs that are going to work just fine on your WebAssembly code, so you still have to fix those things. As an attacker, if you find one of these and you want to do something interesting, look for Inscript and run script, because that's where you're going to have the most fun. If you don't see that, you can use overflows. You can use other things that allow you to write arbitrarily to overwrite values. And in the function pointers cases, you can overwrite interesting things there. If you get XSS, you can turn back around and modify what the Wasm is going to be. And even if there's no XSS because they didn't use Inscript and run script, for example, then you should still be able to modify things in memory that are useful to you. And then if you're talking about Node, then all these tricks turn into RCE. We have a white paper, Security Chasms of Wasm, written by Brian, Tyler, Jeff, and myself. Black Hat site has kind of the version 0.9. We have a couple more things we want to finish, and when we do, we'll put that on the NCC website. So I'm Justin, this is Tyler. Thank you for coming. If you enjoyed our talk, please fill out the survey. If you didn't enjoy our talk, please don't fill out the survey. Our speaker liaison has told us that we don't have to go to the wrap room because it's lunchtime, so we can just take questions here until we're done. Questions? Yes. Yeah, sure.
So if I wanted to debug an x86 program, I'd use like Ollie or IDA or something. What would I use for WebAssembly?
There's actually really good debugger support in browsers now, so both Chrome and Firefox. If you go into developer mode, sorry, repeat the question. He wanted to know how to debug this stuff. If you go into developer mode, you can actually see all of the WebAssembly instructions in S format, which is what we were showing him as. And you can like step through, you can set breakpoints, all that stuff. In Chrome, you can actually see the values that are on the stack at any given time. It's pretty cool. It works really well.
Thank you.
Yeah.
What would you want people implementing other programming languages on top of WebAssembly to know or to think about?
I could only hear half of that. A little louder.
Oh, sorry. What would you want other people implementing other programming languages than C on top of WebAssembly? What would you want them to know or include?
Okay. So if your language is already memory safe, then like a lot of the things that we talked about aren't really going to apply. You need to think about all the existing known vulnerabilities in the language that you have in its kind of base form. And then for each one, just think about how does this apply to the architecture of WebAssembly? Is there something about WebAssembly that makes these vulnerabilities not work anymore? Is there something that makes them more prevalent because of whatever's going on? I think things like deserialization will probably still be an issue. I don't know if there's something as a language developer you can do about that, but it would be interesting to think about. It's not something I've thought about yet.
Thanks.
Thanks. Yeah.
Hi, I'm totally missed during your demo. When you're uploading the file, are you just reading the file contents into that buffer? Or
Yeah, we were copying the file contents directly into it.
into a string or into a char array and just like them and going for it?
Yeah.
Sweet.
After we're done up here, if you want to see the code, we can just show you.
Awesome. Thank you.
Yeah.
Hi, great talk. Maybe I missed it, but
A little louder?
no. Maybe I missed it,
Yeah.
but what happens when you go past the local variables? Like, what do you overwrite in linear memory, or can you even do that?
So the locals can be overwritten. I think, I can't remember how.
Well, it depends on the compiler. So each one is going to be a little bit different in how they implement the various like data structures and stuff in C. But there are other things like outside of your local variables that could be potential targets, depending on the compiler.
Yeah, so like we mentioned, earlier we were able to overwrite literals, which normally, like in other languages, usually you can't do that because they're somewhere else, right? But because of the way that it was laid out at that time, it was working because we could go find it. Now it doesn't work. So a good place for you to start would be to look at that PDF that we linked, because that lays out, they have the entire file format as it exists currently and like where the different sections are and how they work. So that would be a good place to think about that. But at the end of the day, a lot of that stuff is only in the WebAssembly instructions section. And so you can't get to it from linear memory because linear memory is the only thing we can overflow. So I wish I had a better answer for you, but the answer is, 1, it depends. 2, it's probably going to change. And 3, there could still be interesting things there that we don't know yet.
Right. So does that also mean that there's a point in having some kind of stack canary equivalent potentially? As in, you would want to have boundaries between your various linear memory pieces or sections?
Yeah, maybe. I don't know how hard that would be for them to do, but yeah, there's maybe. You also have to keep in mind that we're doing WebAssembly is supposed to be really general, and so maybe something we do for that works well in C, but then it's going to make it harder for them to do things in other languages. So, right. Thanks. All right, no other questions. Thanks.
Sweet. Thanks, guys. Appreciate it.